All right. Well, thanks, Matt, for the introduction, and thank you all for joining, both in person and on Zoom. The title of my talk is Risk Guarantees for End-to-End Prediction and Optimization Processes. And yeah, as Matt said, this is joint work with my PhD advisor, Fatma Kilic-Kazan. Might have to click on this. So before I begin, I just want to advertise this optimization special session at the Australian Mathematical Society annual meeting, which will take place from December 6th to 9th. I'm one of the co-organizers. Min Dao is the other one. And it'll be in Sydney. This is not a picture of UNSW Sydney, but it will be at UNSW. We have keynotes lined up, Kate Smith-Miles and Miguel Goberna. We welcome students and ECRs. So if you want to, I think it's a great opportunity for PhD students and any ECRs to present their research. Tentatively, we have a limit of 25 speakers. Usually the optimization session is one of the large ones. So, we have to leave space for the other people. So if you're interested in doing this, presenting at this conference, please contact myself or Min. Our email addresses are on the screen there. And the deadline to do that is October 15th. Well, you may have seen an email with a link in there where you can submit your expression of interest for that. So you can use that link as well. But if you don't have the link, please contact me and I will forward you that link. Okay, so that's a brief advertisement for that. I'll get started on my talk now. This is the problem, well, a typical optimization problem. It's a linear program, right? We're trying to minimize this linear function C transpose X, subject to some linear constraints, AX less than or equal to B, right? And we notice that these letters that I've made red and bold, these are, this is the inputs to your optimization problem, right? So we typically need these to plug into our model, and then, the computer will spit out a solution. Now, what typically happens in practice for a lot of applications is that these inputs, A, B, and C, are estimated from, well, some methods, like maybe statistics, machine learning, whatever you want, right? And there are a lot of applications for this. I've listed some here. I'm sure you can think of your own. But I'll highlight one, and this one comes from this company called DoorDash, and they're a company in the US that, picks up food from restaurants and delivers to people's houses, right? So I'm sure you've seen similar companies in Melbourne. We definitely have some in Sydney. And one of the key operational problems that they have to solve is driver order matching, right? And so what this means is that they need to allocate which drivers should pick up which orders, right? So at a certain point in time, their drivers, DoorDash calls them dashes, right? DoorDash sees the locations of the drivers. They know which restaurants have orders that need to be picked up, right? And so you can kind of see how far it takes, how long it takes for a particular driver to get to a particular restaurant. And then you see where the customers are, so you know how long it takes from a restaurant to a certain customer, okay? And so now the problem is we need to match the drivers to routes, right? And you may notice that this is a variant of a bipartite matching problem, right? The left nodes are drivers and the right nodes are routes. And what a route is that it's potentially more than one pickup location. So you could be picking, one driver could be picking up from 2 restaurants and then deliver to 2 customers, for instance, right? So that's what happens with this first route, the box on the right here. M1 is merchant 1 or restaurant 1, M2 is restaurant 2, and then after picking up those 2 orders, they may go to the 2 customers, K2 and K1 in that order. And then another route, maybe M3, K3, customer, merchant 3, customer 3, M4, K4, and so on. And, you may have 3 routes, 3 drivers, and then the question is, well, should you tell driver 1 to take the first route or the second route? Should you tell driver 2 to take, you know, which route should you tell driver 2 to take, and which route do you tell driver 3 to take, right? And the way you make that decision is to actually have a score for allocating a particular driver to a route, okay? So this is, you know, bipartite matching problem. In fact, it's not exactly bipartite matching problem, but the spirit of it is quite, you know, similar to that. The only difference is that there are some extra constraints here that you need to impose to make sure that your allocation makes sense, right? I won't get into that. In fact, this is just a screenshot from their engineering blog, right? But the kind of, you know, special sauce that makes this thing work are these edge scores, right? So what's the score? What, you know, score should I put to allocating a particular driver to a particular route, right? And these scores, well, what they say in their blog is that they take into account these ready times, how long it takes for the restaurants to prepare an order, these travel times, you know, how long it takes for drivers to get to orders and deliver them. And these may fluctuate depending on traffic conditions and so on. And also the likelihood that drivers will accept the route. And there's a likelihood here because the way it works is that it's not like the company doesn't tell the driver to do this order. It's more of they offer the route to the driver, and the driver can choose to accept or not, okay? So there's a likelihood involved here, right? Now, the point of this is that, you know, all of these things are estimated via ML models. They don't tell us what they are. I think this is their special source, so they don't tell that to us. And then they're aggregated in some way to form the score. Again, they don't tell us, right? But that's how it works, right? And so if I'm going to abstract this a little bit, then this is the problem we're trying to solve, right? We have an optimization problem to minimize a function f of x plus c transpose x over some constraint set big X, right? I'm not going to touch the constraint set here, right? And I'm also not going to touch this f of x here. I'm going to consider those as known, right? What I don't know are these linear coefficients c, right? So think of these as the edge scores in the allocation problem, right? I don't know those, but what I have is side information or covariates w that will help me predict c, right? So I'm going to predict g of w as an estimate for what c is. And then what I'm going to do is actually solve the problem, except instead of optimizing with c, I optimize with g of w, right? And this approach is, you know, has several names. I think it's fairly straightforward, but, you know, there's end-to-end optimization. People call it that sometimes. Another common name is predict, then optimize, okay? It's fairly straightforward, but one crucial step is, you know, once you decide on a particular prediction method to estimate your C's, right, you want to kind of judge how good your predictions are, right? So if we didn't have this optimization step, maybe one way to judge how good the predictions are is to just measure how close your prediction G of W is to C, right? And you can measure that using, well, here I've stated it as the squared L2 norm, right? Or the squared error, right? That's a very common thing to do. We're going to call this the prediction loss throughout this talk, right? But now that we're in the end-to-end setting, right, where we have a subsequent optimization step, well, perhaps the better way to judge the quality of an optimization of a prediction is to look at the optimality gap, right? So the optimality gap between the solution you obtain using your predictions versus the true solution. So this is just notation here, but X star, the blue X star, G of W is the solution obtained by solving with G of W. And then this big L G of WC is just the optimality gap between using the solution X star G of W and what you could have obtained by optimizing with C. Okay, so you know, in some sense, both of these are kind of measures of proximity between G of W and C, but since we're in the predict then optimize or end-to-end optimization setting, I think the second one makes a little more sense to use. Okay. All right, so let me just give an overview of what a typical pipeline might look like. I didn't mention data before, but there's the question of, well, how do you actually obtain your prediction function? The way you do that is you look at historical data of, you know, covariate and cost vector pairs. So that's WI and CI. They may be distributed according to some distribution P, which you don't see, but you see the data, you see the pairs, right? And you also have new data, W and C, right? In fact, you don't observe C, but you do observe W, right? So you use your historical data to kind of build your prediction model, right? And this is what stats machine learning methods do. And they may build the model in a way that kind of optimizes this so-called prediction performance. So they try to minimize some sense of proximity between G of W and C. Often they take squared error loss, right? And then it's fairly straightforward. You know, plug your W into your prediction model, obtain this solution X star G of W, and then you look at your optimization performance, all right? Now, what's not clear, does that mean? Yeah, what's not clear is the relationship between prediction performance and optimization performance, right? So in the first step here, we obtained our prediction model by kind of looking at this prediction performance. Maybe we said, oh, let's try and obtain it by minimizing squared error, right? Standard least squares regression techniques, right? But now that we have this optimization loss here, we want to know, will the solution to our least squares problem actually have good optimization performance, right? That's the question. Okay. Let me mention some related work. The problem can be viewed as one of stochastic optimization with side information. So the usual setup for stochastic optimization is that you're optimizing a function that's given as an expected value of, you know, a certain random function, right? But now stochastic optimization with side information, it's, you know, you still have that expected value, but now you take the conditional expectation instead, right? And that, you know, kind of introduces some complexity. And there are two classes of approaches here. The first is the non-parametric approach, and the second is the parametric approach. So the non-parametric approach works in the following way, right? You fix a kernel K and you solve this problem. Now, I'm not going to get into details of what this is, but, you know, in broad strokes, it's roughly that you use a kernel density estimate to estimate this conditional distribution, and then plug that into your optimization problem and then solve. All right. The parametric approach is, you know, the approach I just described. We learn a prediction function that gives you point estimates for your unknown vector, and you plug it in. Right. There are pros and cons to both, I guess. The pro to the non-parametric one is that right now the theoretical guarantees are slightly more general. They work for non-linear functions and so on. The bad part is that, you know, to solve the problem, you need to query the entire data set, and, you know, you may not have any explanatory insights if you want them, and sometimes you do, right? The pro for the parametric approach, which is the one I'm going to focus on, is that you just need to store this prediction model, right? And, you know, building these prediction models, G, is actually, there's a lot of research already, right? So we can kind of leverage that research, and it has explanatory insights and so on. But the con is that the theoretical guarantees so far are restricted to this particular structure on the objective function where the uncertainty is localized to this linear part, okay? so anyway, this is the related, these are, you know, just a very high level view of the work in the area. And I cite some references below. Yep.
Is there a part for the non-parametric, non-linear, like the f of xc, that's like the full objective function?
Yeah, so this objective here could be nonlinear in C.
And so with f of x and c.
Yeah. So that's why I write it that way. Yeah, so if you have any questions, feel free to stop me. If not, I'll continue. Okay, so we're going to focus on the parametric approach. I'm going to define some terms here, right? Recall that we're assuming that W and C are randomly distributed according to a distribution P that we don't actually see, but, you know, we can still think about, you know, expectations over this distribution, right? Little l in red here is what I call my prediction loss, right? And I'm going to define something called the prediction risk, which is just the expected prediction loss for my prediction model G, right? And, you know, if we're, a lot of techniques in statistics and machine learning tries to minimize this prediction risk, right? You know, as I mentioned before, there's least squares regression, okay? And in fact, even when we don't know P, right, the theoretical guarantees in, you know, statistical machine learning, statistical learning theory, they actually allow you to have guarantees on this expected loss, right? Even though P is not something we observe directly, we just observe from samples, okay? And these theoretical guarantees are fairly well established, right? Right. On the other hand, right, we're going to define another quantity called the optimization risk, which is just the analogous quantity, except I've replaced little l with big L, the optimality gap, right? And the question is, well, can we apply the existing techniques to solve this, right? Can we adapt what we know from statistical machine learning, statistical learning theory to say something about this optimization risk, right? And what this optimization risk is, you know, the expected value of your optimality gap. So the smaller that is, the better, okay? Now, the problem is that big L, G of W, is non-convex and discontinuous in general, right? And that kind of, you know, throws a spanner in the works, right? Yeah, it's non-convex and discontinuous in general. So you don't get these nice guarantees anymore. And then the other difficulty is that because of this non-convexity and discontinuity, there's actually little theoretical guarantees even for algorithms to optimize this guy. Although, you know, there's been some work recently that tries to do this, and they've shown that it works well empirically, but, you know, there's not much you can say in terms of guarantees. Like, you don't understand the performance at a conceptual level. You just see that on some applications, it works quite well, right? Another argument for maybe not trying to do anything direct is that it may actually be simpler to use an independent prediction method rather than any method that tries to deal with this big L loss directly, right? Because if you're going to deal with this big L loss here, the optimality gap, you need to have an understanding of the optimization problem you're trying to solve, right? You need to know exactly what it is, right? Here's an example, right? So in the footnote, I have f of x is equal to c transpose x plus gamma times some quadratic risk term here, right? This is inspired by mean variance optimization, right? And this gamma coefficient, it's a fixed value, but this is a tuning parameter that people often do when they do portfolio optimization or mean variance optimization, right? But if you're not sure what that is, right, that makes it hard to apply these methods where you need to know, or you need to define the optimality gap exactly, right? And so if you're not sure what to set gamma as, it may be better to kind of use an independent prediction method first and then plug it in to your optimization problem later, okay? Anyway, so this is the optimization risk. And here are some issues for, you know, applying the existing theory to it. One thing that we can kind of almost immediately observe is that actually the prediction risk and the optimization risk have a common minimizer, right? So if you define this function G star of W as just the conditional expectation of your cost vector given W, right? What we'll see, or what we can easily see if we sit down for a couple minutes, is that G star minimizes this optimization risk, and it also minimizes this prediction risk, assuming that you're using the squared the squared error loss, right? So in fact, they have a common minimizer, right? But you know, I'm not sure if that's enough, right? And the reason why I'm not sure if that's enough is because still, you know, even if you're using like a very nice, even if you have a very good prediction model, you may not be able to estimate this this conditional expectation exactly, right? You can never get, you know, perfect kind of estimation of that, right? And that's a problem because X star D is in general discontinuous, right? For instance, for linear programs, right? If you have a cost vector for your linear program, well, okay, first I should explain, this is the polytope defining my linear region, my linear constraints for my LP, right? And then if I have, you know, these two different cost vectors, the blue one and the red one, which point in slightly different directions, right? The minimizer is going to jump from either this blue vertex to this red vertex, right? And even if you make them very close, right, but they're on different sides of this half space that I draw in the dotted one, right? In fact, the two minimizers are still going to be far apart, okay? So what that means is that even if G of W, so you have a prediction method and you estimate C with G of W, and let's say that's very close to the conditional expectation, right? Very close. You don't know that the optimal solutions are going to be close, right? And then you don't know what impact that has on your optimization risk, okay? So that's a problem, right? And now even when X star D is continuous, as I mentioned before, big L of DC is non-convex, which means that optimizing this optimization risk or making it small is actually, well, practically, empirically, there's some evidence that it does well, but you know, it's not established how to do that well in general. Okay, so that's the main source of difficulty, right? So now the question that I want to address is that suppose we settle for building our prediction function using these established methods from statistics, from machine learning that, you know, uses a nice loss function little l, right? If I commit to doing that, the question is, will good prediction performance lead to good optimization performance, right? That's the question, okay? And the goal is to kind of understand the relationship between the two, right? And if I'm able to do that, then hopefully this will help in selecting prediction methods to use, right? So then we understand, well, if we use this prediction method, it may not be so good if we have a subsequent optimization step, right? Or if we use a different one, it may have better optimization performance, right? And hopefully by understanding this, it may lead to the development of new, more effective practical techniques in this end-to-end framework. Okay, so now if we're going to answer this question, we kind of have to ask ourselves, what is the property that a prediction loss function should have in order to guarantee good optimization performance, right? So a prediction method, essentially what it does is that it tries to optimize the prediction risk for some chosen prediction loss function, right? So now the question is, well, how should I choose my loss function, right? Should I choose it to be squared error? But I mean, there's an alternative. I can choose it to be L1 norm between two vectors instead, right? So there are a lot of alternatives there, right? But you know, whatever alternative I choose, intuitively, I should have that approximate minimizers for little l should also be approximate minimizers for big L, right? So if I'm doing very well on my prediction loss, I should also be doing reasonably well on my optimization loss, right? And so let's formalize that a bit. I'm going to introduce some notation here. So I'm going to fix W. Obviously, I'm fixing P, my distribution, and I have some constants delta and epsilon, which are just greater than 0, right? And I'm going to define two sets of vectors, right? The first set, little m sub little l, takes in the argument delta, right? And basically, it just says that this set is all the vectors D such that if I look at the conditional expectation of the little l of DC, right? The conditional expectation is for C, right? If I look at that versus the smallest, versus the smallest conditional expectation I could have had if I were allowed to choose D freely, right? And if the gap between those two is less than or equal to delta, then the vector D here is in my set, okay? So that's my first set, little m sub L. And now my second set, big M sub L, is just the analogous set, except I'm replacing little l in red with the big L in blue there, right? And of course, I changed my threshold to epsilon on the right here, okay? So those are my two sets, right? And notice here that these are sets of vectors, right? So before I was talking about prediction functions G, so mappings between features that give me cost vectors. But now I'm just talking about the vectors themselves, right? Which makes things a little easier to handle, okay? So now the condition I'm going to propose is that it's called calibration, right? So I'm going to say that little l is p-calibrated if for all w and epsilon greater than 0, I'm able to find some delta greater than 0 such that this little m set with parameter delta is contained in the big M set with parameter epsilon, right? And that means that the approximate minimizers for little l, which is my little m set, is contained in the approximate minimizers for big L, right? Which is my big M set, okay? So this is the condition I propose to, you know, kind of formalize the intuition that I had before, okay? And of course, the theorem here is that, you know, if little l is convex in D for each C, right? And it satisfies this calibration condition, then, I mean, this second part here is kind of technical, but at the end of the day, it says that if you have a prediction function G, right, here, right? If you have a prediction function G, and you know that the prediction risk is quite small, right? So the difference between the prediction risk of G and the smallest possible prediction risk you could find, right, is small, right? Then that will upper bound some function of the optimization risk, which is R of G on the left here, right? And that function is given by this eta here, and eta satisfies some nice properties so that this thing actually makes sense, right? So that's the theorem. And of course, to give a little more context on this theorem, this says that for any epsilon, suppose you want to guarantee that your optimization risk is less than or equal to epsilon, right? So suppose you want to guarantee that, you know, the expected optimality gap is only epsilon away from the best possible gap that I could have, all right? That's the thing on the right. Then I need to make sure that the prediction risk gap is less than or equal to delta, right? There will exist some delta where if I can guarantee the thing on the left, I will have the guarantee for the optimization risk on the right, right? And this kind of, you know, boils down to inverting eta in some clever way. And so note here that delta depends on our distribution P that we actually don't know, right? So to get rid of that, I mean, there's a natural generalization of this condition where we, instead of knowing P, we assume that we know a class of distributions, script P, right? And then there's a generalization of the containment condition that we have before. And the difference is that now we require a single delta such that this containment condition works for all W and P in script P, our class of distributions, right? And then the result is very similar. There's another function eta, right? But eta is now independent of your distribution P, and you have the similar relationship between the two risks, okay?
L is still convex like in the previous one, or it's doesn't need the...
I think you don't need it. Yeah, because the proof techniques are slightly different. Check the paper carefully for that, but I think you don't need it. Yeah. Okay. So that's that. All right. I want to make a few comments about these results. Right. The first is that these results are kind of general in the sense that the choice of learning algorithm, right, doesn't actually impact these results. So typically, when you're tasked with building a prediction model, you have to define what your method is, right? And typically that means, okay, let's choose this loss function, right? Well, that does impact the results, right? Choosing the loss function impacts the results. But you also define the class of models that you're going to look at, right? You may look at linear predictors. You may look at, I don't know, neural network predictors and so on, right? And you also, yeah, you look at that, right? And that has an impact on your results, right? In fact, these results, though, are kind of agnostic to those choices, right? And it does not impact the results. So if you go back here, it just says that as long as you have some G that you know to, you know, be doing very well on your prediction performance, right? Then you have, you can be sure that it will also do well on your optimization performance, right? In terms of optimization performance, okay? So regardless of how you obtain G, right? It doesn't matter how you obtain G. As long as you have the G, you can say something about prediction and optimization performance, right? The second one I should mention is the proof idea. I mean, the proof idea is based on this paper by Steinwart from 2007, which considered similar questions, but in the context of ML and not optimization. And the idea is, you know, essentially we want to integrate out these calibration conditions, although we have to be careful to take, you know, you have to take care of some measure theory considerations and things like that. But that's the idea there, okay? Okay, now the next question is, now that we have those conditions on calibration that kind of give us a sense of what these loss functions should look like, right? How do we actually verify these conditions, right? How do we verify that little l is calibrated? And what is the form of eta here, okay? So now, to kind of get a handle on that, I want to introduce another condition called Fisher consistency, right? It's a more common, I mean, there's a name for it, first of all, before I did this research turns out it already existed, right? And it's called Fisher consistency. And what this definition is that instead of looking at approximate minimizers, we're just going to look at the minimizers, right? We look at the minimizers of your little l, your expected value of conditional expectation of little l DC given w, right? And those minimizers on the left should be contained on the minimizers of expected value of big L, conditional expectation of big L, right? So that's Fisher consistency, okay? So now the theorem here is that actually for optimization, Fisher consistency is equivalent to calibration, right? It's actually equivalent, right? So more precisely, a loss function little l is P Fisher consistent if and only if it's P calibrated, right? And actually one direction is fairly straightforward: to go from calibration to go from a condition on approximate minimizers to a condition on minimizers is fairly straightforward. It's actually the other direction that's difficult, right? If you know something about your minimizers, well, minimizers, you know, it's not clear how you give a similar condition on approximate minimizers, right? Because the simple reason being that some approximate minimizers are not actually minimizers, right? But the way we kind of get a handle on that is that we rely on this property called upper hemi-continuity, right? So it's essentially I mean, I said before that the minimizers of an optimization problem are discontinuous in general, but they still satisfy enough regularity, and the sense of regularity is through this upper hemi-continuity here. They satisfy that, and that's enough to kind of give us this result here, right? And roughly, it says that changing D will not change the set of optimal solutions too drastically, and that's enough to give this equivalence here, right? And so what this now allows us is to actually check which prediction loss functions are Fisher consistent. And checking this is actually, I think it's a little easier to do than checking calibration, right? Even though conceptually they're equivalent, right? But I mean, we can do some here, right? Suppose that we have the squared loss. Little l DC is just the squared 2 norm between D and C, right? Then we know that the minimizer, the vector that minimizes expected value of little l DC condition on W is actually the conditional expectation, okay? And so this will be consistent for any distribution, okay? Now, what about L1 loss, right? Then we know that the vector that minimizes this conditional expectation is actually the conditional median, not the mean anymore, but it's the conditional median, right? And that now this is consistent for symmetric distributions, right? One where, well, I mean, in multiple dimensions, there's various ways to define symmetry, but roughly it means that the mean is equal to the median, right? Another loss function that I want to actually talk about a little bit, because I think it's quite interesting. It was introduced by El Maktoub and Grigas, well, back in 2017 is when the preprint first came out. This reference here has 2022 because that's when the paper was published, so it takes 5 years to publish one of these things. But they introduce what's called the SPO plus loss, right? And what the SPO plus loss does is that it's very slick, right? Instead of looking at big L DC here, right? You're going to look at big L and then change the arguments a little bit to be C 2D minus C, right? And when you do that, what it does is that it makes this convex in D, right? And when it's convex in D, that means that you can apply your convex optimization machinery to estimate these prediction models, right? The other thing is that now that you're using the function big L, right, now you have a function that's convex in D, but also has information on the optimization problem built into it. All right, so if you're going to optimize that to get a prediction model, you'd hope that this built-in information on the subsequent optimization problem that you're going to solve with your prediction model, right, is going to do well on that problem. Okay, so this generated a lot of interest, and I think it still is generating a lot of interest, right? And in the paper, they have a result that says that it's consistent for symmetric and continuous distributions, right? But actually, it's not consistent in general. In fact, well, we proved that it's not consistent in general, and it's actually not consistent for fairly, shall we say, you know, fairly natural settings that I'm going to demonstrate in a bit. Okay. And so, well, here's one example where it is consistent. In fact, this example kind of captures the problem of classification, right? So I'm going to set big X to be negative 0.5 to 0.5. So it's actually an interval. So our optimization problem is just a one-dimensional optimization problem. C is just plus or minus 1, right? So if we're thinking about classification, that just means your label is yes or no, or plus or minus 1, right? And now if this is my big X and I'm optimizing, you know, X times D, right? X star D over this set big X is just this. And what that means is that big L DC is just a 0-1 loss for guessing this label, right? So if the sign of D is equal to C, that means you've guessed the label plus or minus 1 correctly, and your loss is 0, right? So you don't pay a penalty. If the sign is different, you pay a penalty of 1 because you got it wrong, okay? And this SPO plus loss is this guy, a max 0 of 1 minus 2DC, right? And you notice that actually this SPO plus loss is something that's known in the machine learning literature. It's called the hinge loss, right? And so for binary classification, big L is 0-1 loss, little l is hinge loss, and that means that SPO plus loss is equivalent to using support vector machines, right? And for support vector machines, we know that it's actually Fisher consistent for any distribution that you want to place on plus or minus 1, right? So that's for binary classification. Things are nice. Oh, except for the distribution that places weight 1/2 on plus or minus 1, right? So for that, yeah, you don't have Fisher consistency, but that's not a very meaningful problem anyway. Okay, so that's good for binary classification. But now if we try and generalize this just a little bit, right? So C now is just some number in some real number, okay? Instead of saying that C is plus or minus 1, let's just generalize it a little bit so that C is some real number. This is what the formulas work out to be, okay? And so now, right, this is the, well, I'm not going to go into detail what this formula is, but it turns out that the D's that minimize this conditional expectation are just all the D's such that the sign of D is equal to the sign of the conditional expectation of C. Okay, so if you plug in a D where the sign of D is equal to the sign of the conditional expectation, right, that's going to make this loss as small as possible. In fact, it'll be 0, right? Now, for the SPO plus loss, it turns out that the set of minimizers is a subset of the set of D's such that the sign of D is equal to the sign of not the expectation, conditional expectation, but now it's the conditional median, right? And so what that means is that this SPO plus loss is Fisher consistent only when these signs match up, right? And so now even just generalizing this condition from before just a little bit, right? What we did was, I mean, before we had C was plus or minus 1 binary labels. Now C is just a real number. Same setup, same optimization problem of optimizing over this interval, right? Now we have a weaker Fisher consistency condition, right? The last example I'll give is, now of multi-class classification, right? So we can frame this as an optimization problem as well, right? So this problem, just a brief overview, is that we want to classify covariates W into one of M classes, right? And so, well, typically we take M to be greater than or equal to 3. If M is 2, then it's just binary classification again, and we already understand that, right? Now X, so M for M greater than or equal to 3, we're going to set X to be the simplex, right? So it's just all the vectors that have non-negative entries and sum up to 1, right? In RM, right? C, well, I'm going to encode my labels in this way, right? So if W has a label J, right? J is one of my classes. I'm going to make the C vector be 1 minus EJ, where EJ is just the standard basis vector. And 1 minus EJ is just 1 in every entry, except it has a 0 in the entry that corresponds to my label, okay? So then now, if I plug in an arbitrary vector D, right, X star of D is going to be equal to EJ, where J corresponds to the minimum entry of D, okay? Now my loss, if I compare D to one of these 1 minus EJs, one of these encodings of my labels, right, it just gives me the 0, 1 loss again, right? It's going to be 0 if the minimum entry of D is equal to my label J, and it's going to be 1 if the minimum entry of D is not equal to J. Okay, and the SVO plus loss, I mean, you can plug it in and check that this is the SVO plus loss. Okay, so that's multi-class classification. That's how you capture it in this optimization framework. Now, what is our, well, I mean, I'm going to add this notation PJ for the probability that I see a particular class J given W, right? I'm going to now ask, how do I minimize the conditional expectation of big L, right? It turns out that the minimizers here are all the vectors D for which the minimum entries correspond to the entries that have the largest probability for my probabilities PJ. Okay, so I'm going to choose. So the best thing to do, I mean, this is the Bayes classifier rule. The best thing to do is to choose the class that has the highest probability of occurring, right? Fairly straightforward, okay? Now, ideally, what we want is that now we want the minimizers for little l SPO plus to be contained in the set of minimizers for expected value of big L, right? So what conditions on my distribution P will ensure that this containment holds? Right? And there are some conditions, but it turns out that the condition is very stringent, right? What you actually need is that the largest probability needs to be greater than a half, greater than or equal to a half. So for instance, if you have 5 classes and your probabilities are 0.49 for the highest class, and then it might be 0.1, 0.1, 0.1, and what's left? 0.21 or something like that, right? For the last one, right? So the highest one is 0.49, right? Even that won't be enough to guarantee consistency, right? Because whenever the maximum PJ is strictly less than a half, what we can show is that the minimizers for the expected SPO plus loss, conditional SPO plus loss, right, is actually just all the vectors with equal entries, right? So for multi-class classification, you can't actually get the right prediction unless you have strong enough signal in your distribution, right? Even when it's clearly strong enough, but if it doesn't meet that 1/2 threshold, then you can't do it. It's going to be inconsistent, right? So that's, you know, that's kind of, you know, one of the pitfalls of using this SPO plus loss. I'm almost out of time, so I should mention briefly that actually I'm a huge fan of this SPO plus paper. I really like it, and they've done something very, very clever. And it feels like I'm critiquing it a lot, but actually I don't mean to. I am a huge fan. Anyway, but you know, these are the you know, theoretical considerations that we have to think about when we use it. Okay. Now I had a section on checking for script P calibration, so this uniform calibration, but I don't think I have time to go through that. Basically, the summary is that it's harder to do, but if we consider a particular class of square integrable distributions, we can do it, and there are some conditions, and you can derive the form of eta in this way. Right, I won't go through that here. What I'll finish off, and I'll leave some time for questions, is that I'll briefly flash up the slides from my numerical study where we kind of tested the theoretical conclusions of this paper. I have 3 classes of problems here: mean variance portfolio optimization, where I use, you know, real stock return data; fractional knapsack, where I simulated some data; and multi-class classification, where I again simulated some data. And remember, for this last one, we know that this SPO plus loss will be inconsistent. And what I'm going to compare are these 2 loss functions: this least squares loss, right, something that's very standard, very easy to do, a lot of research on it, and this SPO plus loss, this somewhat fancier loss that takes into account information, but is quite slick in that it achieves convexity in D, which means we can apply, you know, standard convex optimization solvers to it. Okay, so what happens is that for mean variance portfolio optimization, we see that, interestingly, there's not that much difference between the 2, right? I won't get into details on this due to time, but I'm happy to discuss it offline. Again, with fractional knapsack, actually now we see that least squares is being outperformed, right? And when is it being outperformed? It's actually being outperformed when, well, this is how I simulated the C's and W's, right? The formula at the top here, right? And the least squares loss is being outperformed by the SPO plus loss when the model is nonlinear, right? So one thing I forgot to mention is that actually I'm going to try and learn a linear prediction model using these 2 losses, right? So I'm going to learn the coefficients V here, right? And then I'm going to estimate C with V times W, okay? And so when the model is more nonlinear, which means the delta here is, you know, not 1, right? I see that, you know, the SPO plus loss does a little better, which is interesting. And now the last one, multi-class classification. This is the one that we know the SPO plus loss should do badly in, and it does do badly, right? We see that the SPO plus loss just kind of, the optimality gap, the true optimality gap, just kind of hovers at the top here. It doesn't decrease really, but you see for the least squares loss, it does decrease, okay? And so the conclusions here are that, well, what we've done is that we've given some theoretical conditions which relate prediction and optimization performance, and we gave some methods that allow us to check these conditions. And the numerical results tell us that, you know, these conditions do have an impact practically, right? So they are conditions that we should be aware of, right? So sometimes the simpler least squares loss is more effective than these fancier losses that take into account optimization performance, and sometimes they're not, right? In a case where they're not, we actually don't understand the theory very well, right? So this second example on fractional knapsack has this interesting robustness to model misclassification property, which I think would be very interesting to explore, right? Why is it that the SPO plus loss is robust to using a linear model when the true distribution is a nonlinear relationship between C and W. That we don't understand. Okay, so that's all I have for today.